this is Fiona Fringe. Today we'll be discussing Lab 4 oscillations. Here we have our table of contents. I'll start with introduction and move into fundamental concepts, including applications of Newton's second law and the energy principle, then experimental setup, computational model, graphical comparison, and then discussion questions. The main objective of this investigation was to illustrate the comparison between the motion of an oscillating mass hanging from a spring moving back and forth in the real world versus in a computational model. By applying the energy principle of Newton's second law, we can make estimations about the x and y positions during oscillation. For the quick preview of our results, we found that the observed and computational models trends had similar results. However, the location of the axis in the tracker software may have led to some variance, and the energy was conserved in this investigation. The energy principle is actually quite intertwined with the first law of thermodynamics, saying that the energy cannot be created or destroyed, only transformed, taking on various other forms. The change in energy is equal to the work done on the system by the surroundings plus any thermal energy exchange that may take place. However, in this lab, we are assuming that there is no thermal energy exchange and that work done equals 0, so the energy is conserved in the system. To the right, we can see that the change in energy is equal to the change in kinetic energy plus change in gravitational energy plus change in spring energy, which can also be modified to derive the equation. The change in energy equals 1/2 mv squared plus mg change in y plus 1/2 ks squared. Some additional concepts that should be included is Newton's second law, saying that the change in momentum and net force are proportional to one another. This experiment, the net force is the sum of the spring force and gravitational force acting on the system. The spring force is a non-constant force resulting in deformation or change in distance, and this distance will always be in the same direction as the relaxed length. The spring force can be found as negative k times L minus L naught times L hat, and we can use Hooke's law to calculate the spring constant. We also applied the position and velocity update formulas. For this experiment, the system was the mass, spring, and earth, and the surroundings was anything external, and in this case was nothing. Some important assumptions to make was the Q, or the sum of heat transfer, was 0, and the change in energy would be 0. So for the procedure, we inputted the recording of the oscillating mass into Tracker and analyzed the motion to collect position and time data for the x and y components. Then we edited the starter code with initial conditions of various physics equations, and then I read the program to develop graphs to compare the position displacement between experimental and computational models. Here's the video of the oscillating mass. So for initial conditions, we have that the ball mass was 0.402 kilograms, the initial position was negative 0.111, negative 0.6100 meters, and the initial velocity was 0 meters per second across all components. And then L naught was 0.123, and the spring constant was 6.83, and these were all inputted already into the code, but if you look at the equations at the bottom of this page, you can see how these would be calculated by rearranging the T equation, which is basically the time it takes, and for L naught, we found that by rearranging the force of gravity equals the force of the spring. So for the computational model, I inputted all the initial conditions, the frame rate and time, and critical constants, and at the bottom it has all the different energy equations for the change in kinetic energy, for gravitational energy, and the spring energy, and the sum of all of them together. In the slide, it shows all the equations that we use, including that the force of gravity equals negative mg, the force of the spring equals negative k s L hat, and then F net equals F gravity plus F spring. Those are the only forces that will be in this. And then we also have the position and velocity update formulas, and then at the bottom you can see how we calculated energy changes for all of the different types of energy, and then the sum of all of them together. The animation to the left shows what our x and y data from Tracker would look like compared to the computational model. Initially, the masses overlap for the most part, but then it begins to diverge as time continues due to confounding variables like the real world versus theoretically, such as the idea of an isolated system. We'd also see that in the y position versus time graph, the real model's y component peaks were not as smooth and did not move as far up and down as the theoretical model. These discrepancies may be due to certain sources of uncertainty, including the origin and calibration, that are mass and work done by surroundings. So within Tracker, we may have had issues with the origin and calibration, leading to a 0.100 meter discrepancy between the data sets that were theoretical and experimental. This at our mass, there may have been inconsistencies in data collection when selecting the center of the oscillating object, which would lead to variance in data precision when choosing places for displacement in the x and y directions, and then work done by surroundings I also already touched on a bit. So the real world system is not isolated like a computational model, and there are additional forces acting on the system, including any sorts of air resistance or drag forces. So what does this mean? Is the energy principle satisfied? So yes, the energy principle is actually satisfied because no work is done by the mass spring Earth system. The change in energy equals work, and because work equals 0, it shows that this is satisfied. And in the graph to the right, we can see graphically that the orange line represents the change in energy, which is the sum of the change in kinetic, gravitational, and spring energy is constant, and all the waves for all the individual ones are also constant, going up and down. So for the oscillation estimates, I found that the x estimate was 1.529 seconds and the y estimate was 1.415 seconds. So to find these two estimations of the oscillation periods, I found the amount of time it took for 3 different oscillation periods and divided it by 3 because we were trying to find a good average. And then we found that gravity actually plays a larger role in the y component than x, and y should be used when looking at this oscillation estimate because the spring is actually moving in the y direction, so we'll have more effect.